All right, so what did we learn from Tuesday? So we started buck converter, and to recap, we did the transfer function. We derived the transfer function under three conditions: ideal, steady state, and CCM. CCM stands for, anybody?
Continuous conduction mode.
Continuous conduction mode. So please remember, this transfer function that you see on the screen right here for a buck converter only is valid under those three conditions, right? Ideal, steady state, and CCM, right? Then these are and conditions. This has to meet all those three conditions, right? But even if it's not ideal, you'll be close to this transfer function too, okay? You're just gonna have to compensate a little bit, add a little bit duty cycle if there's losses in the converter, right? But overall, that's the target duty cycle right there. When you design the converter, when you design a DC to DC converter, such as a boost, buck, or buck boost, use the theoretical duty cycle, right? And then you can always adjust later. So for the first phase of the design, use this ideal transfer function. Later on, once you put in more losses in the calculation, and you can compensate those in the equation for the duty cycle, right? So again, one more time, that's the transfer function for buck converter. That shows that this is a step down, because again, average output voltage is equal to duty cycles times V in, right? Given that V in is fixed, duty cycles from 0 to 1, so therefore V out can only be less than or at best equal to V in, ideally. Okay. One very important property of this, I mentioned that last time, I will mention it again here, that this transfer function does not have I out in the equation, which is great news, right? There's no I out. So that means V out, right, is not dependent on load current, only depends on the duty cycle and input voltage. Okay, that's great news, because again, we have power converter, which carries lots of current, lots of big currents, right? And then what else we learned? We learned about voltage, how to apply volt-second balance. Let me go back. We learned about how to apply volt-second balance, and this is something that I would like you to memorize. Where is it? Must be previous page. Oh no. Right, so I want you to memorize this method, or at least memorize how to start volt-second balance equation. For most DC to DC converter, this will be true. That VL on T on plus VL off T off is equal to 0. T on in most cases is going to be dt. T off in most cases is going to be 1 minus d times T. So you only need to find two values, VL on, VL off. That will be it, and you're done. And you could derive the transfer function, the easy way, this way. All right. And then we learned about how to sketch the inductor current waveform. Why is it that it is a triangular waveform? You can see that the slope going up is charging, right? Because it's a positive slope, right? So therefore, it's a charging slope for the inductor. That happens when the switch is on. Keep that in mind. When the switch is on, we are charging the inductor. When the switch is off, we are discharging the inductor. And then I know there's a lot to absorb here. That's why I would like you to review again, if you have time today, that delta IL, what is delta IL equation? Must be right here. Yes, right there, yes. So you can see delta IL, right? Equation, what is delta IL? That's peak to peak ripple. is not a function of I out either, just like V out. Right? There's no I out in this equation. And you can do that, you can derive delta IL either from T on, this is from T on, I can tell from dt. Remember dt is equal to T on. You could also have the equation for delta IL for T off. Right there, right? And the magnitude should be the same for steady state. We discussed that last time as well. How do I know this is from T off? I can tell from right there, 1 minus d times T. Okay. And again, inductor current waveform is triangular waveform. Right there, right? So in steady state, you should see this type of waveform in your buck, boost, and buck boost converter, right? Now, notice that this has peak value, IL max, IL min, and average value, right? Those three quantities, right? And we talked about how to derive the average value. Turned out to be the midpoint between the two critical points, right? Between IL max and IL min. So the midpoint is the average value. Using areas of trapezoids. I mean, you could use different methods, but I use areas of trapezoids. And this is a very important equation. We're going to see this over and over again, right? So let me say this equation now. And again, hopefully I'm hoping that you can remember this equation as well. That IL average is equal to IL min plus IL max divided by 2. Right? You just add those two critical points and then divide it by 2. Right? Basically the average of the two. Right? The midpoint basically. Right? So IL min plus IL max divided by 2. Okay, that's the equation for IL average. And this is only true for CCM. Remember that, okay? Because our analysis for these converters are under CCM mode. Right? So under CCM, this is true, and then it doesn't matter if it's a buck, a boost, or buck boost, this is always true, right? This equation, this is a general equation for buck boost and buck boost. Okay, now for today, okay, again, those are just to summarize what we cover on Tuesday. For today, we're gonna learn how to size these components, right? Now that we know how to analyze the circuit, how the circuit operates, right, with the two states, switch on, switch off. Now, the next thing would be to be able to size the components, because that's what you need when you design a converter such as this one, right? You need to know how to size the inductor, the diode, capacitor, switch, and so on and so forth, okay? Now, the very first thing that you need to size for a buck boost and buck boost is this guy right here. That component right there is a very important component, because that would affect this component, inductor, will affect the operation of the circuit. It will affect how you size diode, how you would size the switch, capacitor, and the rest of the components. So this is a very important first step in the design, is to be able to size inductor. Now tell me what do you need? What kind of parameters do you need to determine to be able to size inductor? Anybody? Come on.
Input and output voltage?
No. I'm saying, what parameters do you need to select an inductor? Maybe the question is wrong. Sorry about that. When you select an inductor, right, eventually you're going to have to buy that inductor, right? So tell me what things you need to know before you can buy an inductor.
Your delta IL that you want?
Sorry, Alan, let me, my speaker is not loud enough. Okay, go ahead.
Delta IL.
Delta IL. So when you buy an inductor, you have to know delta IL. When you look for the data sheet, you look for the delta IL.
Are you asking for the inductance?
Yes. So I'm asking, when you go buy an inductor, what do you need to know?
The inductance.
The inductance, yes. What else? Is that it?
The maximum current the inductor is going to see. You're going to want to make sure it's rated for that.
That's correct. That's it. Okay. All right. So those are the two things you need to be able to purchase an inductor. Right. Same thing for capacitor, diode, a switch. Right. Eventually, you're going to have to buy them. Right. So you need to have some values, right, numbers, before you can go out and select the proper diode, proper switch, and so on and so forth, right? But for inductor, you need these two values. A lot of students know how to do the L. They are familiar with L because that's inductance, right? But for power electronics, IL peak is also very important. In electronics, it may not be, but in power electronics, it is very important. Why? Because in power electronics, we deal with higher currents, right? So you definitely don't want to ignore the IL peak. What if the current exceeds IL peak rating of this inductor? What's going to happen with that inductor?
If it's more than just like a transient, you're going to overheat the inductor or possibly damage it.
Yeah, no, we're not talking about transient, steady state. So what's going to happen? Damage who?
Like the coils in the inductor. The wire is going to get too hot.
Yeah. So what's going to get too hot? Most likely, if you have a DC to DC converter such as this one, it's going to damage either the switch or the diode first before it can damage the inductor, right? What's going to happen is that under non-saturation region or linear region of this inductor, the inductor current, as you know, looks like this, right? Triangular waveform. But if it's under saturation point, if you exceed that IL peak, it's going to look like this. They're no longer a triangular waveform. This is very high peak current, right? And that could exceed the current rating of that MOSFET or the current rating of that diode. So most likely you're going to damage the MOSFET first or the diode first before you damage the inductor. So inductor is pretty, what do you call it? What's the word I'm looking for? A robust, right? Or a very tough component, right? Inductor. Compared to the switch and diodes, these are all very sensitive, more sensitive than the inductor. Okay, so be careful. If you ever see a inductor current that looks like this instead of a triangular waveform in a buck boost or buck boost, that's an indication that you are saturating that inductor. You need to buy a different inductor, or you need to replace that inductor with a new inductor that can handle the current rating. Right. So we're going to talk about these two. Right, L and IL. How do we determine inductance, and how do we determine IL peak? Okay. This is where the previous discussion is important. I see that, man, 1/3 of the class is missing again. That is not good. I hope that they watch the video. Okay, because I'm going to go faster after this, right? I'm going to go through this slowly first time, and I'm going to go faster with this when we go to boost and buck boost. Okay, so first I was going to say that the reason why the discussion on Tuesday is important because you learned that we have a triangular waveform for inductor, right? And then we have IL max and IL mean. In order to determine L, what we call critical inductance, you need IL mean. But when you do IL saturation rating, then you need IL max. So you need both IL mean and IL max. Okay. Okay. But before we do that, let's look at this circuit again, and let me erase this so confuse you. All right, right there. Now for a buck, specifically for a buck, this only is valid for a buck converter. If you look at the inductor current, right there, by KCL at this node, I know that IL is equal to IC plus I out, right? IL of T is equal to IC of T plus I out of T. However, if I am interested in average current only, and we already know how to find the average current of an inductor current, right? That's just IL max plus IL min divided by 2. So if I'm only interested in average quantity, right? We know that by amp second balance, the average current through the capacitor must be equal to 0. So therefore, IL average in terms of average quantity, IL average must equal I out average. Why? Because IC average is equal to 0. Right? That's why in this equation I wrote IL average is equal to I out average. Just in case you're wondering what happens with IC, you should know from this class that IC average is equal to 0. Okay, so I'm not ignoring IC, right? It's just it's because IC is equal to 0. That's why I'm not including it here, right? Because it's 0 anyways. Okay, so that's only true for a buck converter. Now, one thing before I forget, that's why when we learn about buck boost and buck boost, it is important where this inductor is located, right? In a buck converter, the inductor is located at the output side. Remember the T junction, right? The letter T right there. For a buck, it's on the output. That means IL average is equal to I out average. In the boost converter, hopefully we get to see that today, maybe not, we'll see. The inductor is actually at the input side. If that is the case, can you tell me what IL average is equal to? Somebody? Is equal to what current? Whose current? If it's at the input.
So IN average?
Exactly, IN average. Exactly, right? In buck boost, it's in the middle. That's actually more difficult to analyze. But for inductor, for a buck, it's the easiest because IL average is equal to I out average. Why is it the easiest? Because we typically know what I out average is. That's typically given in the design specs, right? Not directly, but typically we are given P out max and V out, right? Typically those are the two values that customers will provide us, right? So from here, if you can, I mean, you can already know that I out is just P out divided by V out, right? So P out divided by V out gives you this. That's why I said it's easier for buck. Because right away I would know what IL average is, worst case scenario, right? If you want to find a worst case scenario or max value of IL average, that's none other than P out max divided by V out, right? But if the inductor is at the input, like a boost converter, then IL average is equal to I in average. So that's why you have to somehow translate all of these output parameters into input, which is not bad either because we assume ideal. So we know that P out is equal to P in, right?
Professor?
Go ahead.
How do you know that IL average equals IN average when half the time it's pulling from the diode? Or for a certain amount of time it's pulling from the diode?
I'm sorry, can you say that? I could not hear you.
How do you know that IN average is the same as IL average when some of the time IL is pulling from ground?
I'm saying if this inductor is right here for a boost, not buck, okay? Forget about this. If the inductor is at the input, right there, like you see here, IL average must equal to IN average, right?
Oh, okay. So we're moving on to boost. Okay, thank you.
That's what I said, right? If in the boost converter, inductor is at the input side. That's why I said earlier, it is important for us to know where inductor is located. If it's located at the output, like a buck converter, is easy. IL average is equal to I out average. If it's a boost, that inductor moves to the input side. If that's the case, then IL average is equal to I in average. Even if there is a capacitor right here at the input, which you will have anyways for a boost, then you can see that IL average is still equal to I in average. Why? Because I know that IC average is equal to 0, right? Does that answer your question? Was it Nick?
Yeah, that answers my question. Thank you.
Okay, good. Now a buck boost is going to be a bit more challenging because a buck boost is going to be, the inductor is going to be in the middle right here. Okay, so that's going to be more challenging. We'll see later. Okay. Now the reason why I'll spend, I don't know, 5 minutes on that, because it'll become important later on. Okay, understanding where inductor is located. Okay, one more time. For a buck converter, IL average is equal to I out average, and we know that I out average is equal to V out average over R of the output, or output resistance. And we know the equation for V out with respect to V in for a buck converter, that's just D times V in. So there's another equation for IL average. And lastly, this is another equation that we derived earlier or on Tuesday for IL average. So now you see multiple equations for IL average, right? Multiple equations for IL average. We first knew about this equation from Tuesday. Now you know more equation for IL average, right? IL average is also equal to I out average, V out average over R out, and then D times V in over R out. Okay. Okay. Any question on that one? So from the triangular waveform, oops, yeah, from the triangular waveform, now you know the equation for IL average, right? Multiple equations. Okay, let's look at the very first parameter L. Okay, there are two different ways to determine critical inductance at L in microhenries, or sorry, in henries. Right, we want to be able to determine L. Okay, the first one is going to be textbook approach, and I still want to go over this because I think it's important for us to go over the textbook method, because this is related to analytical skill, right? And then there's a practical method as well, which I'm covering as well, right? Of course, in the actual design, I usually use the practical method, not the theoretical method, right? If you look at textbooks, they all cover the textbook method. That's what I call the textbook method, because every textbook that I've seen uses the theoretical method, right? Which is what? Using or applying boundary conduction mode, right? Whereas the practical method is very simple, right? Much simpler, okay? But not much analysis though for the practical method. A lot more analysis for the textbook method. Let's go through the first one, right? I'll show you the long way first, as always, and then the simpler way, right? Okay. The first method is using boundary conduction mode, okay? Let's see, right here. Let me just go back here first, right? Okay. Erase this. By now, we already know that the inductor current waveform looks like this, right? Triangular waveform. Now, let's say that the waveform that you see in front of you right there, right? The triangular waveform, that's again, inductor current waveform. That is the picture when the load is, let's say, at full load. Let's just say at full load. Let's say that full load is 10 amps. Let's just say. So this is going to be at 10 amps I out average. Okay. Okay. Now, that means that the average of this triangle is also 10 amps, right? We just talked about it, right? That IL average is equal to IL average, right? IL average is equal to I out average. So if output average current is 10 amps, that means IL average is also 10 amps, right? And keep in mind that average is just the midpoint between the two critical points, right? Between IL max and IL min. All right. Now, what if I decrease the current to 9 amps? What's going to happen with this waveform, do you think? Anybody? What's going to change from that waveform?
Physical.
Will it change the shape?
No, why just shift
Nope.
down a little bit?
There you go. Very good. So because output current now is lower, right? Of course, IL will be lower as well, right? if the output current average is 9 amps, that means this inductor current will also be lower, right? Remember, IL average is equal to I out average for a buck only, okay? Good. The shape does not change. Remember I said earlier that delta IL is not a function of I out. So the shape stays the same. What if I keep decreasing to 8 amps? Then it's gonna keep decreasing as well, right? Just like that. Peak to peak ripple, still the same, because again, delta IL does not depend on I out. So the shape stays the same, delta IL stays the same. Now, if I keep decreasing it, at some point of time, watch, so please pay attention here. At some point of time, if I keep decreasing the output current, eventually this triangular waveform will reach, what do you call this mode? Anybody?
Boundary conduction mode.
Boundary conduction mode, very good. Right? Now, what's so special about boundary conduction mode? And before you answer, this boundary conduction mode right there has an average value, right? Let's call it I out min. And here is I out max. Average value, right? Okay. What's so special about that boundary conduction mode? What's special about it is this, right? Because the waveform just touches zero, right? The IL min point just touches zero. That means, right? That means what? That means the average value, I out min, must be, how do you relate that to delta IL? Anybody?
Would it be ripple over 2?
That's correct. Oh, wait, ripple over 2? No. I out. How do you relate I out min average to delta IL?
This equals delta IL.
It's equal delta IL. No, they're not equal. Delta IL is right here.
Oh, it's delta IL over 2.
That's correct. It's delta IL over 2. Remember that I out average, or not I out, IL average, right? This is the same as IL average, okay? So that, right? IL average min. This is also IL average max. Now keep in mind that the average of inductor current is equal to the IL max plus IL min divided by 2. So the special thing about boundary conduction mode is that the average value of the inductor current, or in this case output current for a buck, is equal to delta IL divided by 2, right? In other words, if I can specify I out min, right, to be a way to determine L, then I would know delta IL, right? I out min means what at BCM. So if I tell you, okay, the converter is going to maintain continuous conduction mode down to 1 amp, let's say, below which is going to be DCM, right? If I keep reducing I out beyond this point, what's going to happen with IL? It's going to be discontinuous, would it? Like this? You all agree with that, right? So then, again, if somebody said, okay, I want this converter to maintain continuous conduction mode down to 1 amp, let's say, what does it tell us about delta IL? Can you tell us what delta IL is if somebody says that?
Smaller than 2?
No. Smaller than 2. Oh, yeah. Or twice, or 2 times 1, right? 2 times 1, because when somebody says down to 1 amp, that means boundary conduction mode is 1 amp average. Does that make sense or no?
Can you say that again?
So if somebody says, okay, I want to maintain the operation of a buck converter down to 1 amp, down to 1 amp means boundary conduction mode to 1 amp. That is average value, right? 1 amp. The average value is 1 amp. What does it tell us about delta IL for a buck?
2 amps.
2 amps, exactly. That means if I out min at BCM is 1 amp, that means delta IL must be 2 amps. Yes? Anybody has any question on that one? Okay. Now, now what if I change instead of 1 amp? I'm going to say, okay, I changed my mind. I want to say I want to have a buck converter that would maintain continuous conduction mode down to 2 amps. Right? That means average of 2 amps. Average current of 2 amps. What does that mean in terms of delta IL?
4 amps.
4 amps. Right? If I out min at BCM is 2 amps, that means delta IL must be 4 amps. What I'm trying to say is that now you see the relationship between I out average at BCM and delta IL, right? The bigger the I out min at BCM, the bigger the delta IL, right? You see that, hopefully? Now, that's the first point. The second point, this is getting crowded here, so I'm going to erase some of these. Now, I'm going to use green now. Okay, now if I change, right, the peak-to-peak ripple, now I'm going to do the opposite effect here. Now I'm going to have my triangular waveform to be this way. You see that? At full load. I don't know if I can draw it maybe this way. Yeah. So look at the green. Let me erase this one and this one. Right, I'm trying to draw my best there, such that the average value of the green right here is equal to the average value of the blue, right? So still 10 amps at max, at full load. Both of them are 10 amps average, you agree? What is the difference there? Obviously, the difference is delta IL, right? So now you can see that you could achieve the same average value with different ripples, right? You could have different peak-to-peak ripple and get the same average value. That's my point. Now, if I have a bigger ripple, peak-to-peak ripple, which one do you think is going to reach boundary conduction mode faster or earlier? Is it the bigger peak-to-peak ripple or the smaller peak-to-peak ripple?
Bigger.
The bigger, yes. Now, this is going to be the difference right here. I'm going to erase the blue here, if I could. Come on, yes. So that you can see the red, which is coming from the blue, right? And then the green, I'm going to stick with the green. Is it still green? Yes. If I keep decreasing the output current, the green is also going to be shifting down, right? At one point of time, the green will also, the minimum of the green right there, IL min will also touch BCM, just like that, right? You see that? Now, can you tell me the average value of the green with respect to the average value of the red? Which one is larger?
Green.
The green's larger.
The green is larger. What does that tell us? It tells us that if you have a small peak-to-peak ripple, you have a wider range of output current, right? You can go lower in terms of boundary conduction mode than having a big peak ripple. Am I correct on that statement? Because the average of the green is higher, meaning you have less range of output current before it goes to boundary conduction mode, right? Is that clear?
The trade-off for this is that the inductor gets larger if you want a smaller.
Not yet, but yes, but not yet. Okay, I just want to go through this slowly. So that's correct. But do you agree with that statement? That the bigger the peak-to-peak ripple, right? The smaller it is for you to be able to have the range of output current. right? Okay. If peak-to-peak ripple is 0, right? Imagine if that triangular waveform becomes flat, right? That means you could go down to 0 amps, right, before it reaches boundary conduction mode, which we know is not going to happen, right? But that would require infinite inductance. Anyhow, so now the next question is, how do we relate delta IL with L, right? Because we know that delta IL right there, peak-to-peak ripple, affects the operation of our circuit, affects, for example, how the circuit maintains CCM. Now, why is it maintaining CCM important? Anybody?
So the transfer function holds?
Very good, excellent, excellent. Because we want that transfer function to hold. I mentioned on Tuesday, if it goes to DCM, then the transfer function V out over V in will be a function of load, not nice anymore, right? So we want to have an operation of the circuit where the output voltage is not a function of load. It's not a function of current. In order to do that, we need to maintain CCM as much as possible, right? Don't you want that, right? So that's the desired goal, of course, right? But how can we achieve that? How would we be able to maintain CCM as much as possible? By maintaining lower boundary conduction mode, right? So how do we do that? Here's the equation. So this is analytical skill, as you can see, right? What we just talked about is using our circuit analysis and analytical method to look for the equation here. Okay.
Professor?
Yeah.
Before you touch that, can you scroll up? I just had a question.
Okay. What is it?
So, sorry, can you scroll up more to what we're, yeah. What point were you making where you said I out average min equals 2 amps and then the delta IL is 4 amps? Like, were you just saying that delta IL is 2 times the I out average min?
What I'm saying is that boundary conduction mode is special, right? Right here, this is boundary conduction mode. It's very special because why? Because the average value right there is always half of delta IL, right? So if you know this value, if you know the average value at the boundary conduction mode, you would know delta IL. That's the statement I'm trying to make. So if, let's say, at BCM, the average is 2 amps, then can you tell me what delta IL is?
Oh, okay.
What is it?
The average at the minimum is 2 amps?
Yeah.
Maximum is 10?
No. Just focus on this. Focus on this. Right? If the average of this waveform, remember this is 0. At minimum is 0, right? That's 0 amps right there.
Yeah.
Okay. Now, if the average of this waveform is 2 amps, can you tell me what delta IL is? What this delta IL is?
Is it just 2 times the average?
Yes. Yeah, we discussed that earlier, right? That's what's special about BCM.
It's always the case that the I out average minimum times 2 is your delta IL.
Okay, you got to be careful, okay? I need to correct that a little bit. That's only true if it's BCM.
Gotcha.
Right? That's what I said earlier, right? What's special about BCM? BCM is where IL min touches 0, right? And then remember, average current is equal to IL min plus IL max divided by 2. Remember that, right? In this case, IL min is 0. So therefore, I know that IL average for boundary conduction mode is always IL max divided by 2.
Okay, cool. Thank you.
Or in this case, delta IL. Our IL max is going to be delta IL because, again, IL min is 0, right? So yeah, make sure that that's clear. Is that good?
Yeah.
Okay, all right. Now, how do we select this L based on delta IL, right? We know that that's the key right there, delta IL. The bigger the delta IL, the more limited, right? The output current operation is going to be in order to maintain CCM, right? So in that case, since we are basing it off boundary conduction mode, right there, and so I know that IL min will be a good boundary condition to look at, right? Because I know for sure that at boundary conduction mode, IL min must equal to 0. I know for sure, right? That at boundary conduction mode, IL min is equal to 0. I don't know what IL max is. That would depend on delta IL, but I know for sure IL min is always equal to 0 at boundary conduction mode. So I'm going to look at IL min equation. So that's the reason why I'm using IL min equation, because later on, right, I know that I could replace IL min with 0 at boundary conduction mode. Hopefully that makes sense, right? So IL min is equal to IL average minus delta IL over 2, right? So if I draw my triangle again, maybe over here, right? If this is the IL, if that's the average, and here's delta IL, I know that IL min right there must equal to IL average minus delta IL over 2. Anybody disagrees with that? Right, so that's what I start, that's how I would start the equation right there. And IL min, again, this is only true for a buck. Okay, I cannot stress this enough, because you know I don't want you to apply the same thing for a boost or buck boost. This is only true for a buck. Okay, IL min is equal to I out min, right? We talked about it, right? That IL average is equal to I out average. So therefore, IL min average is equal to I out min average. Good. Anybody still not clear about this one?
I had a quick question.
Yes.
Right here, why is that IL average min and not just IL average?
Because we're looking at boundary conduction mode. Isn't that the lowest IL average?
Oh, okay. Yeah, that
right?
makes sense.
Remember, we keep decreasing the load, right? So this is the lowest average current you can get, right? For BCM. If you keep decreasing it, you're gonna get discontinuous conduction mode if you keep decreasing it. Does that answer the question, Nick?
Yeah, thank you.
Okay, so that's why I replace IL min. Sorry, that's why this is IL min condition, not max but min, right? And then we know that I out min is also equal to V out average over R out max. V out is always constant, right? We regulate the output voltage. The V out is constant, almost constant, and then R out for min has to be the max resistance, right? It's the inverse. And then delta IL, this is going to be a magnitude or absolute value. You could get it from T off or T on. Remember the equation for delta IL for T on and T off. This one, which one do you think I'm using? I'm using T on or T off equation for delta IL. I'm testing your analytical skill now.
T off.
T off, why?
1 minus D.
Very good, very good. Excellent. Awesome. So now I know that just by looking at the equation, I know that I'm deriving delta IL from T off. How do I know that? From here, 1 minus D times T. We know that's T off, right? Okay, then at the end you get the equation for IL min equals to this equation right here, right? Awesome, that's what we get from IL min. Now, remember boundary conduction mode, right? Now that we have the equation for IL min, I know that at boundary conduction mode guarantees that boundary conduction mode guarantees that IL min is equal to 0. So I just plug in IL min equals to 0. Equals to I out min minus all of these terms. Look at what happens here on this equation. There's an L there. Isn't that what we want to get? So I'm going to solve for L. And that L, whatever we get, is going to be L at BCM. You agree? That L that I get there is going to be L at at boundary conduction mode. Right? So now I solve for L. I call it LC. Stands for critical inductance. And from there, I get LC is equal to all of these, right? Just solve for L. Okay, and here's the equation again. Oh, sorry, this is the equation for using T off, right there. You can tell that from this equation that critical inductance, which is in henries, you're gonna need this, right, to size the inductor, is a function of frequency, right? Also a function of I out min right there. Remember I said down to 2 amps, down to 1 amp. That's where you put in right there, right? And frequency here is also important because it's inversely proportional to frequency. What does that mean? Now you know one reason. Another reason why we want to increase switching frequency, right? Now you know another reason is that if you increase the switching frequency, guess what happens with L? It's going to get less, right? You're going to reduce the size of L by increasing frequency. Reducing L means smaller inductor. Okay, that's another benefit of increasing frequency. I could also use T on for the equation instead of T off right there. And the equation is for LC is going to be right here for, or if you use T on. And it doesn't matter which equation you use. It doesn't matter if you use the T off or the T on. It will give you the same value. Okay. So once LC is calculated, then pick an L value higher than LC, say 10% or higher for safety margin. Okay. Any question on that one? Okay, so you have the equations for critical inductance. Now you do know how to size the inductance. Here's an example. A 60-watt buck converter has input voltage of 10 volts, output voltage of 6 volts, and switching frequency of 100 kilohertz. Calculate the critical inductance if the CCM is maintained down to 20% load. Right? It doesn't give you amps, but it gives you percent. Right? 20% of load. Load means full load right here. Right? 20% of full load. What is our full load? Can you tell me? Oh, try not to look at the answer. What is our full load here? Come on.
60 watts.
60 watts. Okay, what we need now is amperage, right? So yeah, it is true. It's 60 watts, but what does that translate to?
10 amps.
How much? Sorry.
10.
It's 6, right?
6 or 10.
Because output voltage is 6, so I assume output current would be 10.
That's correct. Yes. So output voltage is 6 volts. Output wattage max is 60 watts. So 60 divided by 6. That should be 10 amps. So what's 20% of 10 amps? That's going to be 2 amps, right? So that means I know that I have to maintain CCM down to I out min average to 2 amps. In buck converter, I out min is equal to IL min in buck. Okay, not for boost, not for buck boost. So that means what? This would give you delta IL. What is delta IL? What is it? Come on.
1 amp.
Oh, you always do it the reverse. There you
4 amps?
4 amps. Right? If IL mean average is 2 amps, that means peak to peak is 4 amps. Yes?
Yep.
Okay, okay. All right. So we know delta IL from there. Right? And yeah, it's not being asked here what delta IL is, but this is just plug in chug, as you can see, right? But I want you to understand that just by having this statement right there, it tells me what delta IL is, right? Which is 4 amps. Okay. All right. So I have enough information from the duty cycle and the current that we already found out earlier. And then I just do a plug-in chuck right here using T on equation. We got 6 microhenries from T off equation, as you will expect. It has also the same value. So it doesn't matter if you use T on equation or T off equation, it should give you the same value. All right. Now, of course, when you go buy this inductor, if it gives you 6 micro, I would of course go higher than this, right? So the actual L that you buy must be larger than LC. Why? Well, because in real world buck boost in real world converters, you're going to have losses. right? This equation is based on ideal, no losses at all. So make sure that you pick something larger than the calculated inductance value. So I would maybe, I don't know if there's a 7 micro or 8 micro, right, Henrys that you can purchase, but anything larger than 6 micro. Okay. Any questions? All right. That's the long way of doing this, right? As you can tell, I spent what, maybe 20 minutes or so to try to explain to you how that works, right? Let's do the practical way, and you're gonna love this, right? Because this is the short way, this is the more practical way, this is how most, not most, but all engineers I know in Silicon Valley do in terms of, this is what they do in terms of selecting inductance. And we know that, that delta IL affects the operation of the circuit. It affects how much range we can get for CCM, right? We already talked about it earlier, right? So why not just use delta IL equation straight form? VL is equal to L dIL dt, right? Right here, right? So I know that VL is equal to L delta IL delta T. I have the L right there, and I have delta IL right there, right? So why not use this, right? I know what delta T is, right? Depending on whether or not you want T on or T off. If it's T on, it's dt. If it's T off, it's 1 minus d times T. And I should also know VL, depending on the topology, right? If it's T on that we are using, if we are using T on, then what is VL on equal to, right? We know that that's going to be V in minus V out from Tuesday, right? Remember this? If you use T off, then VL is equal to V out, right? So why not use this, right? Straight from this equation. So that's what we do here. See that? This is using on time. Am I right? Yes. See that D right there? That's coming from the on time. All right. So now LC is equal to delta T on. So just solve for L from this equation, solve for L. And you get this equation right here. And that's it, right? That's it. And then you can also use the off time, right? You use the same equation, but use off time. So same thing, right? You get this equation right there. I should probably box in this one too, right? This is from on, this is from off, right? So just remember VL is equal to L delta IL delta T, which you've heard thousands of times, right? During your EE career here in at Cal Poly. Just remember VL is equal to L delta IL delta T, and then solve for L, right? And then the rest is just it's just going to be a matter of finding out what VL is, right? And then determine what delta IL you want to get, right? So if you look at this equation, let me erase this. If you look at this equation, for example, the first one, right? The first one right there, you would know what duty cycle is, right? How? Because we typically know what V out is and what V in is. Right? If you're designing a buck converter, you must know what V in is, and what V out is. That's why you should get duty cycle. V in, I just told you, you should know that. V out, you should also know that, right? How about frequency? That's another thing that you have to pick. If it's not given by the customers, then you have to pick. So select, a switching frequency, right? Let's say 500 kilohertz. Sometimes you don't have any choice. Sometimes it is determined by a controller. Controller will say, fixed switching frequency. So use that frequency, right? If not, if the controller says, if the controller data sheet states that it's a variable frequency from such frequency to another frequency, then go ahead and pick one frequency for now. Right? You can always optimize later. Right? So the only thing that's left to decide is delta IL. And we know from our previous discussion that delta IL determines how low IL min is, right? The bigger the delta IL, the larger I out min you get. The smaller the delta IL, right? The bigger range you get for the output current. before it reaches DC boundary conduction mode. Right? So this is something that you have to choose. And in practice, this is what they told me. Right? We choose between 30% and 40%. Right? Of what? Of IL max. So delta IL is in between 30% to 40% of how do you do this? Of IL. This is delta IL. This is the wrong statement. So I should put it this way. So delta IL should be in between. There you go. 40% of IL max average and 30% of IL max average. That's it. Right? Very simple. How do you find IL max average for a buck converter? Do we know what IL max average is for a buck converter? Do we know this value? Anybody?
Data sheet?
Huh?
It's
Data sheet? Or
the
no?
average output current plus half the ripple.
Remember, in a buck converter, what is IL average equal to? In terms
max.
of, yes, in terms of output
Delta
current.
L divided by 2.
In terms of output current, IL max, IL average is equal to I out average, right? Now think about when you're designing this. Would you know what I out max is? Would you know
max load, right?
Say it again.
It's going to be your max load.
Yes, it is exactly. So this is something that you would know when you're designing it. You have to know because typically P out max, as I said earlier, is given as well as V out is given, right? Just like that example that we had earlier, 60 watts at 6 volts, right? From there, we know what I out max is. And for a buck, knowing I out max will give you IL max. Make sense? Any question on that one? So that's how we do it. That's at least my friends working for semiconductor companies, that's how they usually select L, is by using this simpler equation, simpler approach. They just say, okay, just pick between 30 to 40% of IL max average. Okay, and depending on the topology, you would know what IL max average is. In a buck converter, IL max average is equal to I out max average. Any question on that? No? All good? You sure? I wish this is I wish I'm in the classroom with you because I could see your faces. I don't like it, I don't like to go to the next section if I still see,
See the face of confusion.
Faces are still puzzled, still like confused. Unfortunately, I could not see your faces, so my apology for not being able to give you, what do you call it, real-time feedback on whether or not, based on your faces, of course.
I think it all makes sense so far.
I could proceed or not. Okay. Everybody good? Feeling good about this? Yeah. So 2 methods, delta IL, doesn't matter which one, but I usually go with this one. Right. You can see the equation is simple, but what goes behind it is not, right? We just spent 40 minutes discussing the, what goes behind these equations, right? And the previous one as well. So I'm glad that you were able to make it today to the class, right? That way you just don't plug in Chuck. You understand what goes behind this equation, right? Good. Let me proceed then. I'll let you review that again, right? That's why it's important for you to review this after class. And if it's still confusing, I have office hours. Only a few people take advantage of it so far. It's a good, opportunity for you good time, for you to ask questions during office hours, right? Especially concepts, right? And I'm big with concepts, as you already learned from your first midterm, right? I just don't want you to plug in Chuck without knowing what's going on, right? Okay. Inductors, all right, so that's just L. Now we'll do the IL saturation, which is easier. So we just got done with knowing how to determine L in Henrys. Now is the time for us to know how to size the inductor based on peak current, based on the saturation current of the inductor. Okay, how do we do that? Well, we want to make sure that IL sat that you pick of the inductor has to be larger than IL max of the inductor. This is no longer average value, okay? This is instantaneous value. That's the IL max I'm talking about. This is not, so IL max is not equal to IL average max, okay? IL average, just the average. This one is the actual peak value. Okay. Any question on that one? Okay, so how do we know IL max? So we have the equation for IL max right here. IL max, which is IL peak, is equal to I out average for a buck only. Notice that I change IL to I out. Why? Because we have a buck. Because I know that I out average, IL average is equal to I out average, right? So this is average value. You see that average quantity plus delta IL divided by 2, right? Again, if you have a triangular waveform right there, then I know that the peak value must be the average value. That's the average right here, the middle point, plus delta IL over 2, right? That's how you find the peak value. Okay, and now you can already tell that delta IL equation, you can use T on or T off, right, from Tuesday. Again, now you know that this is coming from T off because I have 1 minus D right there. So I use T off equation. Why do I like to use T off? Because it only uses V out. If you change it to T on, you're gonna have to use V in as well. Remember T on, remember VL on for a buck converter is equal to V in minus V out. So to me, the less parameter you use in the equation, the better. That's why I like to use T off for buck because we only need to use V out. Okay. So here's the equation for IL max. Notice that in order to find that peak value, I need to apply worst case scenario, right? In our case, worst case scenario for the peak value must be at full load, right? If I go back to here, just to make sure that it's clear, right? Come on, right there. Ah, come on. Okay, right there. Erase this whole thing. Erase, 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 erase. Imagine I am changing the output current, right? I could change it from max value to min value. Every single one will have IL max. You see that? That's IL max at full load. That's IL max at boundary conduction mode, which is our minimum load, right? Multiple values, infinite values of IL max. So for using that equation earlier, which IL max do I use? Which one do you think is giving you the worst case? Okay, come on. Not trying to be tricky there. Which one is the worst case scenario for IL max? Is it from the max or from the min?
From the max, probably.
Oh yeah, right. Because when you use inductor, you want in the inductor to be able to handle the worst case peak current, right? The worst case peak current. This is not the worst case of the peak current, right? At minimum load, that is not the worst case. This is the worst case, right? At full load, right? Obviously, this IL max at min, right? It's going to be less than IL max at full, right? So that's why here I put I out max average. Oh, where is it now? Right, that's why I put max right there to signify that this comes from full load, right? This means full load. Full load. Any question on this? All right, so once you get IL max, then as I said earlier, go ahead and pick the inductor whose IL sat is larger than IL max that you calculate. Okay, you calculate IL max and put it right here. Make sure that IL sat is larger than IL max. And here's an example of a table that I got from a data sheet of an inductor. Notice that it has I sat rating right there. So do not ignore this anymore. Okay, now you're into power electronics, right? You're choosing inductor for power electronics. You need to pay attention to this part of the table, right? Before you only care about this, maybe, right? The inductance value. Now you have to have two things to consider: inductance value as well as saturation point. Any questions?
What are those numbers under like the 5.7, the 4.95? Are those in amperes? Yeah.
Yeah, these are all amps. See, that's the unit, amps right there. Switch voltage and current ratings. I'm going to do the voltage, not that bad. The current is the one that's going to take a bit more time. So let's look at the current. Not bad at all, too. Current, I'm going to use KCL, right? Here's buck converter, right? Just the power stage, just the three components. By KCL at that point, I know that I switch plus I diode is equal to IL. Yes. So by KCL, I know that inductor current with respect to time must equal to I switch with respect to time plus ID with respect to time. Right? And I know that inductor current waveform looks like a triangular waveform. This is why it is important. I spent time on Tuesday to explain to you why we have a triangular waveform, right? Now we know that inductor current waveform is triangular waveform. Another thing that we know from Tuesday is that the charging slope happens when what? Is it when the switch on or when the diode is on? Anybody?
When the switch is on?
Very good. When the switch is on, we are charging the inductor. When the diode is on, we are discharging the inductor, right? So I know for sure that when the switch is on from Tuesday, when the switch is on, diode is off. It's always the opposite, right? When the switch is on, diode is off. When the diode is on, switch is off. So just from that statement, it should be easy for us to derive or to sketch the current waveform for a switch and diode, right? Let's start with the switch current. I know that this charging slope occurs when the switch is on. When the switch is on, diode is off. So let's start with diode. Diode is going to be 0 because it's going to be off, right? So it's going to be 0. So therefore, by KCL, I know that diode current plus switch current must equal to inductor current, right? Since diode current is 0, therefore, the entire current that you see here during charging slope must come from switch. Good? All right. So then what happens when we turn off the switch? When we turn off the switch, that means what? Switch current is equal to 0, obviously, right? There's no current flowing through the switch if it's open. So I know for sure that when the switch is off, which is right here, right? Then switch current must equal to 0. If that is the case, by KCL, diode current plus switch current is equal to inductor current. Well, switch current is 0. So therefore, the entire current that you see in the inductor must come from diode. Now it should make sense to you why switch current looks like that and diode current looks like that. Any question on that one? Not bad, right? Okay. Now when it comes to sizing currents for both switch and diode, this is why chapter 2 is still important. You need to calculate the average values of these currents, right? So now it's just a matter of finding the average of this waveform, the average of that waveform, average of this waveform for sizing current rating of the switch, and then average of this diode waveform, IF average later, to be able to select the diode current rating, right? Do we know how to find the average of these currents? You should, right? These are all trapezoids, right? So you can find the area of the trapezoid and then divide it by T, right? We know that the base here is T on, the base there is T off, right? T on is dt, t on if, t of is 1 minus d times t, right? Oh, yeah, this is good. See this examples of data sheets from MOSFET, looks like it is MOSFET. That ID right there, when you pick a diode, you have to know the current rating of that diode. That current rating on the very first page, that is average value, okay? Not RMS, not peak, that's average value. Okay? Same thing with IGBTs right here, right? You see this? This is the first page on the data sheet, top right corner. That 450 amps, that refers to average value. So that's why it's important for you to be able to calculate average value of these waveforms, okay? All right. And then instead of, yeah, I think this is how I do it with the trapezoidal current. So you can see that by using trapezoidal method, right, area under the curve for the switch, you can see that I just used the area under the trapezoid, which is the sum of the parallel sides, right? Sum of this and this. We know that's IL min, we know that's IL max. So IL min plus IL max multiplied by the width, which is T on, and then divided by, times 1/2, and then divided by the period. That's how you get the area of the trapezoid, right? So basically that's what I have right here. Area of the trapezoid divided by the period. And then that ends up with this equation. I know I only have 1 minute here. Okay, so now look at this equation. I like this equation. Look at this part of the equation. Have you seen that before?
That's the average output current.
Or in general, what is the equation equal to? You said output. That's only true for buck.
The inductor current.
Inductor current. We know that part of the equation is none other than IL average. So now I can replace that portion with IL average right there. See this? IL average. It turned out to be that the average current through the switch is equal to IL average times duty cycle, right? And for a buck converter, you can replace IL with I out. Okay, can you, this makes sense. Why? Because this is referring to switch, right? And as we know, duty cycle belongs to the switch. Can you guess how this equation change? How this equation changes when I look for I diode average? How would this equation change? Instead of IL average times D, it's going to be IL average times
1 minus
D. Yes. Take a look at this one. I'm going to skip ahead to diode average right here. Oh, yeah, right there. See this? For diode is IL average times 1 minus D. Okay, that makes sense because diode takes on the turn off portion of the current, the inductor current. Okay. All right. One more thing before we adjourn. The voltage is not that bad at all. How do you determine the voltage rating of a switch? Well, has to be when the switch is open, right? Because when the switch is on, it's going to be practically 0 volts. Same thing with the diode, right? You find the voltage rating of the diode when the diode is off, right? So what is the voltage across the voltage? What is the voltage across the switch? Sorry, when the switch is open. What is the voltage across the switch when it's open? When the switch is open, diode is on. So what is the voltage across the switch? Anybody?
VN.
VN, exactly. Right? Just find the simplest loop. That's the simplest loop right there, right? Obviously, from that loop, we can see that KVL is by KVL, V switch is equal to V in. What happens? And then I'll stop after this. What happens when the switch is on and the diode is off? Come on. I'm trying to do this fast. This is on, this is off. What is the voltage of that diode when it's off? Anybody? Come on.
VN.
VN, yes. If this is off, use that loop like here again. That voltage across that diode is also equal to VN. So that's how you would size the voltage rating of the MOSFET as well as the diode, right? That the MOSFET voltage should be the maximum voltage of the switch or MOSFET will be VN max, right? So you pick a MOSFET whose voltage rating is larger than VN max. Same thing with the diode. When you pick the diode, make sure that the voltage rating of the diode is larger than the input voltage right there. That's for the diode. Okay.